Welcome, AXOR, Galactic Observatory. Tonight, the journey begins with a simple question that opens into one of the darkest and most fascinating truths in all of space science. How long would it really take to travel 1 light year with the technology humanity has now? And what does that answer reveal about our future among the stars? In this documentary, the story moves through the true scale of interstellar distance, the limits of modern spacecraft, the promise of fusion and antimatter propulsion, the strange effects of time dilation, and the haunting possibility that humanity may never truly escape the solar system. This is a calm exploration of science distance and the fragile reach of human ambition beneath an endless sky. Before settling in, please take a moment to like the video, subscribe to the channel, and turn on notifications so you do not miss more relaxing journeys through the universe. Now let the silence of deep space slowly unfold. Far beyond the familiar orbit of the moon, beyond the slow paths of the planets, beyond the drifting boundary where the sun's influence begins to thin into the wider dark space, opens into a scale that does not fit easily inside ordinary thought. The human mind handles hills, oceans, cities, and even continents, with some effort because these belong to the world of direct experience. It can also handle the distance to the moon or to Mars by turning those places into destinations on a chart, points on a screen, names in a story of exploration. But a light year belongs to a different category. It does not feel like a route. It feels like an abstraction, a number placed so far outside daily life that it risks becoming almost decorative, like a label attached to the sky, rather than a real measure of separation. Yet it is real. A light year is simply the distance that light travels in 1 year through empty space. It is not a measure of time. It is not a poetic phrase. It is a length, and that length is immense beyond ordinary comparison. Light itself moves through the vacuum at nearly 300,000 kilometers each second, or about 186,000 miles each second. In the time a human heart completes, a single beat light has already traveled farther than many people will go in months of movement across the surface of Earth. In 1 second, it could circle the equator many times. In 1 minute, it could race past the moon and continue onward. In 1 hour, it could cross distances that once seemed reserved for myth. Then the seconds continue to add together. They become minutes, hours, days, months, and a full year of uninterrupted motion. The result is 1 light year, a distance of about 9,460,000,000,000 kilometers, or about 5,880,000,000,000 miles. Written on a page, the number can be stated in a breath. Lived as a journey, it becomes almost incomprehensible. This is the first hard truth of interstellar travel. The stars do not only appear far away, they are far away in a literal, physical, measurable sense that does not soften under optimism. Even the nearest star system beyond the Sun, Proxima Centauri, lies more than 4 light years from Earth. A single light year, then, is not even the full trip to the nearest star. It is only the first unit in a much larger distance, a first wall in a corridor of walls. From Earth at night, stars seem modest. They fit between tree branches, above rooftops, over fields and oceans. They shimmer quietly, almost gently. They look as though they belong to the same world as clouds and mountains. But that appearance is deeply misleading. Their calmness is an effect of distance. Their closeness is an illusion created by light arriving cleanly across emptiness. The sky gives the impression of a ceiling. In reality, it is an abyss filled with separations so extreme that ordinary travel loses meaning. This is why the idea of 1 light year matters. It is the point where the romance of the night sky begins to meet the arithmetic of the universe. A person can look upward and feel that the stars are part of a reachable frontier, as oceans once were to sailors. But oceans, for all their danger, still belonged to one world. A ship crossing water remained inside the same planetary home, under the same sun, within the same envelope of air and life. Interstellar space offers no such continuity. It is not a long sea voyage. It is a passage through a cold emptiness where distance itself becomes the dominant fact. To understand one light year is to begin understanding that the universe is not merely large. It is structured around separations so vast that they challenge the ambitions of any species that grows on a planet and builds with matter, fuel, and time. This does not make the stars less beautiful. If anything, it makes them more beautiful, because beauty seen across a true gulf carries a different weight. The light arriving tonight from some distant point has crossed darkness for years before touching an eye or a telescope. It has traveled faithfully through silence while empires rose and vanished on Earth, while languages changed, while generations lived entire lives unaware that a beam from another sun was still on its way. In that sense, the night sky is not only a display of objects, it is a record of distance translated into light. Every star overhead is also a message about delay, about separation, about how slowly reality itself can arrive from one place to another. That is why one light year serves as more than a unit. It is a lesson in proportion. It reveals how small the human sphere remains inside the wider cosmos. It shows that leaving a planet is not the same as escaping local confinement. It suggests that a civilization may become skillful, intelligent, and technically advanced while still remaining bound to a very narrow neighborhood around its home star. This realization can feel harsh at first. It strips away the easy confidence created by fiction and replaces it with something more sober. The stars remain present, visible, and inviting, yet the invitation comes with conditions written into physics rather than politics or desire. One light year stands as the beginning of that contract. It says that any journey between stars must first confront the plain fact of scale. Before engines, before fuels, before theories of advanced propulsion, there is this distance silent and unmoving, waiting to be crossed. It does not care about hope. It does not shrink for ambition. It simply exists a measured span in the dark, and by existing, it defines the challenge. The dream of interstellar travel begins here, not with motion, but with stillness, with the recognition that the universe is built on lengths so enormous that even 1 year at the speed of light becomes only a first step into the vast outer structure of reality. When the scale of 1 light year settles into clear view, the next instinct is almost automatic. The mind reaches for speed. If the stars are unimaginably far, then perhaps the answer lies in going unimaginably fast. Human history often solves distance with velocity. Roads shorten when engines improve. Oceans shrink when ships become stronger. Continents feel smaller when aircraft rise higher and move faster. This habit of thought is natural, and within the human world it often works. But the first serious confrontation with interstellar travel begins when that familiar logic is extended into space and then begins to fail. The failure does not happen because humanity lacks cleverness. It happens because the fastest machines ever built are still slow when placed against the distances between stars. This is not a poetic statement. It is a measurable and rather uncomfortable fact. The Parker Solar Probe, one of the fastest human-made objects ever launched, reaches extraordinary speed by falling deep into the sun's gravity well. At its greatest velocity, it travels hundreds of thousands of kilometers per hour, fast enough to cross nations in moments and circle Earth in a fraction of the time of ordinary flight. In the context of the solar system, that speed is astonishing. It represents decades of engineering navigation, thermal protection, and careful use of planetary gravity. It is a genuine triumph. Yet, when compared to the speed of light, it remains only a tiny fraction. At that pace, traveling 1 light-year would still require many centuries. The number changes somewhat depending on the exact speed used, but the lesson does not change. A machine that seems almost unreal by earthly standards barely begins the journey on an interstellar one. Voyager, moving outward for decades after its grand tour of the outer planets, offers another perspective. It is among the most distant human artifacts, a patient emissary drifting beyond the major worlds and into the outskirts of the Sun's domain. It carries memory symbols and the marks of a species announcing itself to the dark. But it also carries a hard lesson in kinematics. Voyager has traveled for many human lifetimes in technological terms, and even after all those years, it has covered only a tiny fraction of a single light year. Its achievement is not failure. It is precisely the opposite. It shows what human engineering can do when made durable, efficient, and resilient across deep time. Yet by showing that it also reveals the scale of the barrier. If one of humanity's most successful long-distance spacecraft remains so close, cosmically speaking, after decades of travel, then the stars are not waiting just beyond the next technical milestone. They stand behind a much larger threshold. This is why the phrase fastest spacecraft can be misleading. It sounds final, as though reaching the top of one ranking means approaching the goal itself. But a record inside one regime may mean very little in another. The fastest fish is still slow compared with a bird. The fastest bird is still slow compared with an orbiting object. In the same way, the fastest spacecraft ever built remain creatures of a local environment, designed within the energy budgets, materials, and mission architectures of a civilization that still works mostly inside one star system. Their greatness is real, but it is local greatness. Interstellar distance belongs to another level of comparison. This becomes clearer when speed is translated into time. A journey that takes centuries is already difficult to imagine as a mission in the ordinary sense. A journey that takes tens of thousands of years leaves the human frame almost entirely. Funding cycles, careers, governments, languages, institutions, and even civilizations do not naturally persist across such spans. A craft may continue, but the mission that launched it dissolves into history. Intentions fade. Names are forgotten. The machine enters a time horizon where the main challenge is no longer navigation alone, but meaning. What does it mean to send something toward a destination that no living person will ever witness it reach? This question sits quietly behind every discussion of current spacecraft and interstellar ambition. It does not weaken the technical accomplishment. It deepens the contrast between local exploration and true star travel. In the solar system, even very long missions still belong to a humanly graspable future. Signals return within practical delay. Images arrive. Discoveries can reshape the understanding of the same generation that built the instruments. With interstellar travel at present speeds, this continuity breaks. Space ceases to be merely large and becomes temporally remote. Distance turns into a separation not only of place, but of eras. This is why the comparison between light and machines matters so much. Light is not only fast, it defines the natural pace at which the universe communicates across empty space. When a spacecraft moves vastly slower than light, it is not simply taking longer than the ideal. It is operating in a fundamentally different relationship to cosmic distance. Light crosses the gap in a year. The spacecraft may require centuries, millennia, or more. That difference is not a technical inconvenience. It is a transformation of the whole idea of travel. The familiar image of a voyage with departure passage and arrival begins to stretch until it almost loses coherence. Yet this stage of understanding is important because it protects the conversation from fantasy. It grounds the dream in real hardware, real trajectories, and real numbers. It says that before speaking of future propulsion, one should first look honestly at what exists now. Humanity already knows how to send machines far from Earth. It already knows how to build probes that survive cold radiation and long silence. It already knows how to use gravity patience and precision to gain extraordinary reach. But this knowledge, impressive as it is, has not yet carried humanity out of the first shallow layer of the cosmic ocean. The fastest probes remain near the shore of the stars. They move with brilliance and endurance, but they do not yet move with the speed required to make interstellar journeys part of normal mission planning. Their trajectories, therefore, teach humility. They are not evidence that the barrier is almost solved. They are evidence of how high the barrier truly is. Every hour they travel, every signal they send home, every additional increment of distance quietly repeats the same message. The universe permits movement. It even rewards ingenuity. But it does not give up its scale easily, and the machines now crossing the dark on behalf of Earth remain, for all their elegance and courage, slower than the human imagination first hopes when it turns toward the stars. Long before modern spacecraft begin threading through the outer solar system, human thought turns toward more forceful ways of leaving home. If chemical rockets are too weak for the stars, and even the fastest probes remain bound to spans of centuries or longer, then the temptation is to reach for a deeper fire, something far more energetic than ordinary fuel. In that search, nuclear propulsion emerges not as fantasy, but as one of the earliest serious attempts to think on an interstellar scale. The reason is simple. Nuclear reactions release vastly more energy per unit of mass than chemical ones. In the language of propulsion, that matters almost immediately. A spacecraft capable of drawing from nuclear processes does not merely improve an existing design. It begins to enter a different class of possibility, where the ratio between carried mass and delivered energy shifts in a way that chemical systems cannot easily match. Yet, from the beginning, this power arrives with an unease that never fully disappears. The same physical process that promises larger reach also brings danger, fallout, political fear, and the uncomfortable fact that some of the most energetic ideas in spaceflight are close cousins to weapons. One of the clearest examples is nuclear pulse propulsion, most famously studied in the 20th century under concepts such as Project Orion. The basic idea is startling in its directness. Instead of relying on a continuous stream of exhaust from a conventional engine, the spacecraft would eject small nuclear devices behind itself and detonate them in sequence, using the repeated blasts to push against a massive pusher plate and accelerate the craft forward. It sounds brutal because it is brutal. It replaces elegance with raw impulse. Yet from a purely physical standpoint, it is difficult to dismiss. The energy available from such detonations is enormous. Theoretical studies suggest that very large payloads could be accelerated far more effectively than with chemical propulsion, perhaps even to velocities that begin to make interstellar travel seem less absurd. For the first time, the imagination sees a machine not creeping outward, but striking its way through the dark with repeated nuclear blows converting destructive force into sustained motion. That image carries a strange dual quality. It is both ingenious and unsettling, a reminder that the line between exploration and violence can become thin when the required energies are extreme. The engineering problems are formidable. A pusher plate must survive repeated exposure to intense radiation and shock. The timing of each detonation must remain precise. The structure of the craft must absorb enormous stress without tearing itself apart. Shielding must protect any payload, whether instruments or people, from radiation and mechanical punishment. Even if solutions exist in principle, they lead toward a spacecraft that is large, heavy, and difficult to test in any ordinary sense. But the technical barrier is only part of the problem. Nuclear pulse propulsion collides almost immediately with political and moral constraints. Launching nuclear explosives from Earth, or even assembling such systems in near space, raises fears that extend far beyond engineering. Treaties limiting nuclear tests, public concern about contamination, and the broader shadow cast by the nuclear age make such proposals deeply controversial. A technology may be physically plausible and still remain culturally unacceptable. In that sense, nuclear propulsion reveals a second truth about interstellar travel. The barrier is not only the laws of physics, it is also the kind of civilization required to use extreme energy responsibly, if such responsible use is even possible. Related nuclear concepts take a less explosive form. Nuclear thermal propulsion, for example, heats propellant with a reactor and expels it at higher efficiency than chemical rockets. Nuclear electric propulsion uses a reactor to power electrical systems that drive efficient thrusters over very long periods. These approaches are less dramatic than pulse propulsion and far more compatible with existing engineering culture. They promise improvements that matter especially for missions within the solar system. They can shorten travel times, increase payload mass, and reduce dependence on purely chemical stages. Yet, when measured against one light year, they still reveal the same sobering pattern. Better does not mean enough. A reactor can extend reach and improve performance without crossing the gulf between planetary travel and true interstellar capability. Even so, the presence of nuclear ideas in this discussion is important because they mark the first serious place where propulsion begins to scale upward toward the energy demands of the stars. They show that ordinary fuel chemistry is probably not the path out. To go farther, humanity may need to work with the deep structure of matter itself, drawing from forces that sit closer to the heart of atomic reality. But that requirement changes the ethical atmosphere of space exploration. Rockets cease to be mere machines of combustion and become systems that handle concentrated, dangerous forms of power, each demanding a degree of technical maturity and restraint that cannot be separated from politics. Nuclear propulsion therefore lives in a tension between promise and prohibition. It is one of the first propulsion families that sounds strong enough to matter for interstellar thinking, yet it is also one of the first to reveal that not every technically serious idea becomes a socially viable one. This tension matters because interstellar travel is often discussed as though the challenge is only to invent a better engine. In practice, a species must also decide what risks it accepts, what infrastructures it can sustain, and what forms of power it trusts itself to carry beyond its home world. A civilization capable of building a nuclear spacecraft is not merely solving an engineering problem. It is making a statement about governance, safety, and the acceptable cost of ambition. This is why nuclear propulsion occupies such an important place in the path outward. It is the moment when the search for speed begins to press directly against the political character of the species doing the searching. The stars remain distant, but now the obstacle is no longer distance alone. It is the kind of power required to confront that distance, and the fact that the first credible answers arrive wrapped in the same force that has already taught humanity how dangerous its own intelligence can be. In that sense, nuclear propulsion does more than offer a path. It reveals the price of taking the problem seriously. To reach beyond the slow margins of current spacecraft, humanity may need engines built on energies that transform not only the vehicle, but the ethical burden carried with it into the dark. Not every path away from the planets depends on violence detonation or the concentrated drama of explosive force. There is another style of movement in space quieter and in some ways more elegant, built not around sudden bursts of power, but around patience. Electric propulsion belongs to this slower category. It does not try to overpower distance all at once. Instead, it works by producing a very gentle thrust over long periods, steadily nudging a spacecraft faster and faster through the emptiness. In the conditions of space where there is almost no drag to erase, gained speed, this approach makes practical sense. A small acceleration, if maintained for weeks, months, or years, can become substantial. This is why ion engines and related electric thrusters have earned serious attention. They use electricity to accelerate particles and expel them at very high exhaust speeds, achieving an efficiency that chemical rockets cannot match. The thrust is tiny, often so small that it would feel almost negligible in an ordinary human setting. Yet over long durations, that faint push accumulates. It is the logic of persistence rather than force, and within the solar system, it can be remarkably effective. Missions using ion propulsion have already shown that a spacecraft can reshape its trajectory with graceful precision, while carrying less propellant than a conventional design might require. In an environment where every kilogram matters, efficiency becomes its own form of power. This makes electric propulsion deeply attractive to engineers. It promises endurance, flexibility, and the ability to keep accelerating long after a chemical stage would have burned itself empty. When joined to a reactor rather than solar panels, the concept becomes nuclear electric propulsion, where a spacecraft carries a nuclear power source that feeds electrical thrusters continuously over long spans. This arrangement is especially compelling in regions far from the sun, where sunlight weakens and solar arrays become less practical. A reactor offers steadier energy. Electric thrusters offer efficient use of that energy. Together, they create a propulsion architecture that seems mature, serious, and more compatible with long missions than many speculative alternatives. Yet, when measured against 1 light-year, a difficult truth emerges again. Efficiency is not the same as speed. A craft driven by electric propulsion can be extraordinarily careful with its propellant and wonderfully disciplined in its motion, but it still accelerates slowly. Over the vastness between stars, slow acceleration becomes a kind of destiny. Even if the spacecraft eventually reaches impressive velocity by the standards of present missions, the journey remains very long. 1 light-year is so distant that a method celebrated for efficiency within the solar system begins to look almost fragile when extended into interstellar ambition. The engine is not failing. It is simply facing a scale too large for thrift alone to conquer. This distinction matters because electric propulsion often feels like the most rational path forward. It avoids the political terror of nuclear explosions. It avoids some of the extreme storage problems associated with more exotic fuels. It grows naturally out of existing technologies. It belongs to a recognizable engineering culture of measured improvement and system reliability. For all these reasons, it may become one of the most important propulsion families for building a larger human presence throughout the solar system. Cargo missions, deep space probes, infrastructure transport and robotic exploration all stand to benefit from engines that sip propellant and operate steadily for long spans. But the same qualities that make electric propulsion attractive also reveal why interstellar travel is such a different problem. Inside the solar system, there is room for slow elegance, because the distances, though immense, still belong to a bounded neighborhood. Between stars, slowness becomes inheritance. A voyage lasting centuries or longer is no longer only a transportation problem. It becomes a civilizational one. If a machine is sent alone, then the question becomes whether its instruments, materials, and power systems can persist across spans longer than most institutions survive. If people are sent, the challenge grows much deeper. A vehicle moving by gentle thrust toward another star may become a world in transit, carrying not passengers in the ordinary sense, but generations. Children may be born aboard it, live aboard it, and die aboard it, without ever seeing either the departure world or the arrival world, except through records. The mission ceases to be a trip and becomes a lineage. This is where electric and nuclear electric propulsion shift the conversation inward, away from engines alone, and toward time as a lived condition. 1 light year traveled slowly is not merely a long route. It is a transformed human situation. Everything changes under such duration. Food production becomes ecology. Maintenance becomes culture. Education becomes mission continuity. Governance becomes a problem of stability across generations that did not choose the voyage but inherit it. Even identity begins to drift. The people living aboard such a craft may regard themselves less as travelers than as residents of a moving habitat whose destination is almost mythic, a place known through teaching rather than memory. In this way, a quiet engine reveals a loud implication. Propulsion methods that seem practical on paper can push the consequences of travel into realms far beyond mechanics. A gentle thrust spread over centuries does not only move a vehicle. It stretches human intention across time until intention itself becomes difficult to preserve. There is also the issue of power. Nuclear electric systems require reactors that must function reliably over extraordinary durations. Waste heat must be managed. Components must resist degradation from radiation and fatigue. The entire system must remain repairable, or at least fault-tolerant, far beyond the timescales of current spacecraft. None of these demands are impossible in principle, but each adds mass complexity and fragility. The more carefully one thinks through the requirements, the more interstellar travel begins to look less like a single invention waiting to be discovered, and more like a stack of hard problems, each one resting on the others. Electric propulsion solves one layer well. It offers disciplined use of energy. It offers longevity of thrust. It offers a form of motion beautifully suited to vacuum. But it does not make 1 light year small. It simply changes the terms on which that distance is endured. That endurance may prove valuable. It may even become the basis of far future systems that move quietly and persistently between remote outposts. Yet, in the present imagination, it serves another purpose. It teaches that a serious engine does not automatically produce a humanly convenient journey. A spacecraft can be efficient, resilient, and technologically mature, while still taking so long to cross the dark that the meaning of travel itself begins to dissolve into succession maintenance and inherited time. Among the serious ideas for leaving the slow regime of current spacecraft fusion propulsion holds a particular place because it feels like the first concept that belongs partly to the future and partly to known physics. It does not require abandoning established science. It does not ask for new laws of nature. Instead, it asks whether humanity can learn to control, contain and direct one of the most powerful reactions already understood. Fusion is the process that powers stars. In simple terms, light atomic nuclei combine into heavier ones and release energy in the process. The Sun does this under immense pressure and temperature held together by gravity on a scale no machine can reproduce. On Earth, researchers attempt controlled fusion in entirely different ways, using magnetic fields, compression, and carefully shaped pulses to push matter into conditions where nuclei can overcome their mutual repulsion and join. The challenge is severe, but the principle is not mysterious. Fusion is real. It happens throughout the universe. The question is whether it can be transformed from a difficult laboratory achievement into a practical engine. This matters for interstellar travel because fusion offers a tempting balance. It promises far more energy than chemical propulsion while avoiding some of the profound cultural and technical burdens associated with continuous nuclear explosions or the impossible storage demands of more extreme concepts. In the hierarchy of imagined engines, fusion often appears as the first door that may someday open without requiring a leap into outright speculation. That is why it carries such weight in discussions of the stars. A fusion-powered craft could in principle produce exhaust velocities much greater than those available to ordinary rockets. It could sustain powerful thrust while carrying fuel that does not immediately belong to the realm of fantasy. Designs studied over decades, including pulse-based fusion concepts and more continuous reactor-driven ideas, suggest that a spacecraft might reach a meaningful fraction of the speed of light. Even a modest fraction changes the character of a one-light-year journey. At speeds far above anything achieved by present probes, travel times begin to move from many centuries towards spans that, while still difficult, become imaginable within human history. This is the threshold where interstellar discussion starts to feel less like mythology and more like a hard engineering frontier. A one-light-year trip that might take decades rather than millennia remains an enormous undertaking, but it belongs to a timescale that institutions records, and perhaps even individuals could in some form recognize. Fusion therefore represents a psychological change as much as a technical one. It is the first major propulsion family that seems capable of compressing the abyss into something that still feels like a voyage rather than an inheritance. Yet this promise should not be mistaken for simplicity. Fusion is attractive precisely because it is difficult in a disciplined way. It demands precision on an extreme level. A fusion spacecraft must ignite reactions, reliably direct energy into thrust, efficiently manage colossal heat shield-sensitive systems, and carry fuel in forms that remain stable, dense enough and practical over long durations. Every part of that sentence contains its own mountain of unsolved detail. On Earth, controlled fusion remains a major scientific and engineering challenge, even before the added burden of spacecraft constraints is considered. A ground-based reactor may rely on large facilities, extensive support systems, and mass that would be impossible to carry into deep space. An engine for interstellar travel must do much more with much less. It must be compact enough to launch or assemble, robust enough to survive, and efficient enough that the mass of its own support systems does not erase the advantage gained from the reaction. Fuel choice also matters. Different fusion reactions have different requirements and different byproducts. Some are easier to ignite but produce difficult radiation. Others are cleaner in theory but far harder to achieve. A spacecraft designer does not simply ask how much energy fusion can provide. The designer must ask what form of fusion can be started controlled, repeated and translated into motion without overwhelming the machine itself. This is where the elegant simplicity of the basic idea begins to blur into a network of constraints. Even so, fusion remains distinctive because its barriers, while enormous, do not obviously violate known physical law. The problem is not that fusion propulsion seems impossible in the deepest sense. The problem is that it may require a level of technological maturity far beyond what is now routine. This difference is important. Some propulsion concepts fail because they depend on unknown physics or on matter behaving in ways not supported by evidence. Fusion does not fail for that reason. It stands in a harder but more hopeful category. It waits behind mastery. A civilization that becomes truly skilled at controlling high-energy plasmas, advanced materials, heat, rejection, long-duration automation, and deep space system maintenance may eventually be able to build such engines. If that day comes, 1 light year would no longer look entirely unreachable. It would still be daunting. Radiation would still matter. Shielding would still matter. Reliability would still matter. The environment between stars would remain hostile. But the tyranny of sheer duration would begin to loosen. That is why fusion so often appears at the center of realistic hope. It does not make interstellar travel easy. It merely makes it less absurd. There is also a symbolic power to the concept. A species born on a planet orbiting a star eventually learns to imitate in a small and controlled way the reactions taking place inside stars themselves. That image carries a deep narrative force. It suggests that interstellar travel may require not just better vehicles, but a change in the level at which a civilization engages with nature. Chemical rockets use rearrangements of electrons in molecules. Fusion reaches into the nucleus. To go farther, the species must operate deeper. This fits the broader pattern of the problem. Every step toward the stars seems to demand movement inward into more fundamental energies. Yet fusion also teaches restraint. Because it feels plausible, it tempts exaggeration. It can easily become the engine of every imagined future. But serious thinking resists that temptation. Even with fusion, the stars do not become near. They become less distant. That difference matters. 1 light year may shift from impossible to punishing, from unimaginable to barely manageable. Such a shift would be historic. It would transform the horizon of exploration. Still, it would not cancel the fact that interstellar space remains a realm where every gain in speed is purchased with extraordinary effort. Fusion therefore stands as the first real hope, not because it guarantees success, but because it narrows the gap between aspiration and physics, enough that the journey can be discussed in concrete terms without leaving science behind. If fusion feels like the first serious door that might someday open, antimatter sits farther down the corridor, like a source of almost unbearable brightness, attractive in theory and deeply punishing in practice. The idea appears again and again because the underlying physics is extraordinary. When matter and antimatter meet, they annihilate and convert their mass into energy with unmatched efficiency. No chemical fuel comes close. No ordinary nuclear process releases such a complete transformation. In pure energy terms, antimatter seems almost ideal, the kind of propulsion source that would allow a spacecraft to carry far less mass while accessing far greater power than conventional systems could ever provide. For interstellar travel, this matters immediately. The great burden of rocket design is that a spacecraft must carry the means of accelerating itself, and the more propellant it carries, the more propellant is needed to move that propellant, creating a harsh compounding problem. Antimatter appears to strike directly at this burden by offering enormous energy from extremely small quantities. In the abstract language of equations, it looks like a path toward velocities that begin to challenge the long tyranny of distance. A 1 light-year journey that is hopeless under chemical propulsion and still punishing under many advanced concepts can seem newly negotiable when antimatter enters the discussion. This is why it retains such hold on the imagination. It offers not just improvement, but compression. It suggests that the scale of interstellar travel might be reduced without abandoning known physics. Yet almost every practical step beyond that elegant idea turns severe. The first problem is production. Antimatter does not exist in useful quantities waiting in tanks or underground reservoirs. It must be created particle by particle in high-energy facilities, and the amount humanity has ever produced is tiny beyond ordinary intuition. The process is energetically expensive, technologically demanding, and astonishingly inefficient when judged against the amounts a propulsion system would require. It is one thing to create minute traces for experiments. It is another to imagine manufacturing enough for a starship. The gap between those two realities is immense. Even before storage is considered antimatter, propulsion asks a civilization to become capable of producing and collecting an exotic resource at a scale that now belongs far beyond industrial experience. Then comes storage, perhaps the most famous and unsettling of the barriers. Antimatter cannot be placed in an ordinary container because touching the walls would destroy it immediately. It must be suspended isolated by electromagnetic fields in an ultra-controlled environment. The system must remain stable over long periods. It must survive vibration radiation, thermal fluctuation, and the endless unpredictability of real machinery. For a laboratory experiment, that demand is already difficult. For a spacecraft crossing deep space carrying enough antimatter to matter, it becomes a long-duration challenge with very little room for error. A failure would not resemble a simple leak. It would be an instantaneous release of enormous energy. In this sense, antimatter does not merely ask for precision. It asks for a form of precision so complete that ordinary engineering language begins to sound too casual. The machine must behave almost perfectly, because the consequences of imperfection are catastrophic. Even if one imagines production and storage eventually becoming manageable, there remains the question of how to turn annihilation into useful thrust. Energy alone is not motion. A propulsion system must direct that energy, shape it, and prevent too much of it from becoming destructive radiation rather than effective acceleration. Some antimatter reactions produce highly energetic particles and gamma rays that are difficult to channel. Shielding a vehicle and its contents against that environment adds mass. Managing waste heat adds complexity. Controlling reaction rates adds another layer of system delicacy. The engine therefore becomes not just powerful, but temperamental. It must tame one of the most intense physical processes accessible to known science, and do so repeatedly, safely and efficiently inside a moving spacecraft. This is where antimatter begins to reveal its true nature. It is not merely an advanced fuel. It is a demand for a civilization operating at a level of control that makes even fusion look comparatively grounded. Yet, it would be too simple to dismiss antimatter as fantasy. the idea remains physically meaningful. Nothing in the basic science forbids it. Matter and antimatter do annihilate. The energy is real. In principle, a sufficiently advanced technological society might indeed find ways to produce, contain and use antimatter in quantities far beyond anything now achieved. If that happened, 1 light year could be crossed at speeds that pull the problem out of the realm of generations and back towards something closer to a mission. But the phrase, "if that happened," carries enormous weight. Antimatter does not wait behind one breakthrough. It waits behind many. It requires energy infrastructure, manufacturing capability, field control materials, performance radiation management, and operational discipline all at once. It may be physically possible and still remain practically unreachable for centuries, perhaps longer. That is what makes it so fascinating in the context of interstellar travel. It occupies the narrow band between impossibility and absurd difficulty. It is not forbidden by nature, but nature offers it with no generosity. Every advantage comes attached to a near-matching burden. The elegance of perfect mass-energy conversion is balanced by the ugliness of real containment. The promise of extreme speed is balanced by the cost of building and surviving the engine. For this reason, antimatter serves as an important lesson in the larger argument about 1 light year. Greater energy does not simply solve the problem. Greater energy changes the shape of the problem. As propulsion grows more powerful, the journey may become shorter, but the machinery becomes stranger, more hazardous, and more demanding of technical mastery. The obstacle shifts from duration alone to a broader question of whether a species can wield such concentrated power without being defeated by the conditions required to store and direct it. Antimatter therefore stands as a vision of almost pure propulsion, an answer so potent that it exposes the limits of human engineering by contrast. It hints that the universe may permit faster passage between stars, but only for civilizations capable of building systems of extraordinary refinement and surviving their own success in handling energies that even in tiny amounts carry the force of disaster. If antimatter represents extreme stored energy, laser sail propulsion represents a very different strategy, one that tries to escape the burden of carrying so much energy aboard the spacecraft at all. This shift is profound. Most rocket concepts, whether chemical nuclear fusion-based or antimatter-driven, assume that the vehicle must take its power source with it in some form. That assumption creates the old and difficult mass problem. Fuel adds weight. More weight demands more energy. More energy often requires more structure, more shielding, more control systems, and still more mass. Laser sail concepts attempt to step outside this loop by separating the vehicle from the energy source. Instead of placing the driving power on the spacecraft, they place it far behind, sending intense beams of light toward a sail attached to a very small payload. The light itself carries momentum, and when it strikes or reflects from the sail, it can push the craft forward. The effect is tiny for ordinary light under ordinary conditions, but with extremely powerful laser arrays and an exceptionally lightweight sail, the push becomes meaningful. Over time, the craft may accelerate to extraordinary speed. This is why concepts such as breakthrough starshot receive attention. They suggest that tiny probes, perhaps no larger than chips attached to delicate sails, could be driven to a significant fraction of the speed of light and sent toward nearby stars within travel times measured in decades rather than millennia. In the language of interstellar travel, that is a dramatic compression. For the first time, 1 light year begins to feel not just theoretically crossable, but potentially crossable by hardware designed within an advanced but not wholly magical civilization. Yet the promise comes with a severe narrowing of what counts as a spacecraft. Laser sail propulsion works best when the payload is made very small, very thin, and very light. This is not a system naturally suited to carrying heavy instruments, robust shielding large communication systems, or people. It is a strategy of radical miniaturization. The craft survives not by being strong, but by being slight enough to accelerate under the pressure of light. That makes it elegant, but it also makes it fragile. A tiny probe moving through interstellar space at enormous speed faces a harsh environment. Even the thin gas and dust between stars become dangerous at such velocities. A small particle striking the craft could carry destructive energy. The sail itself must endure acceleration from intense laser illumination without deforming, melting, or losing stability. Guidance must remain precise across astonishing distances. Communication back to Earth from such a small and distant object becomes another major challenge. The probe may reach another star system, but sending meaningful information home across light years with limited onboard power is no trivial task. This is why laser sails, for all their brilliance, do not solve interstellar travel in a general sense. They solve a narrower problem. They may allow extremely light robotic scouts to cross the dark quickly, but they do not easily offer a path for large exploration platforms, cargo transport settlement, or return journeys. The return problem is especially revealing. A sail pushed by lasers from the home system can accelerate away, but slowing down at the destination is much harder. A probe traveling at a substantial fraction of the speed of light will not simply arrive and pause. Without a comparable braking system or a complex environmental method of deceleration, it may rush through the target system at high speed, gathering only a brief torrent of data during a flyby. This still has enormous scientific value. A few moments of close passage through another star system could transform human knowledge. Yet, it is a very different vision from the older dream of a spacecraft arriving, entering orbit, and exploring in depth. Laser sail concepts teach that interstellar success may come first in forms that are partial, asymmetrical, and unmanned. Humanity may not begin with great starships. It may begin with almost weightless messengers that cannot stop. This matters because it changes the emotional shape of the problem. The old image of space travel often centers on vessels carrying crews into the unknown, with destinations approached deliberately and landscapes studied at length. Laser sails offer a colder and more modern alternative. The vehicle becomes nearly invisible. The mission becomes data rather than presence. The journey may be fast, but the encounter may be fleeting. Even so, such concepts deserve their place because they expose a clever truth about propulsion. Sometimes the path forward is not to build a stronger engine, but to redesign the mission around what energy can be delivered externally. This is a profound engineering reframing. It suggests that the challenge of 1 light year may be approached not only by changing the spacecraft, but by changing the infrastructure surrounding it. A civilization that can construct vast, precise laser systems in space or on planetary surfaces is doing more than launching a probe. It is building an interstellar transportation architecture, one where the vehicle and the power source are no longer inseparable. That is a serious shift in thinking. But it also reveals dependence. The spacecraft becomes tied to the existence and accuracy of a distant beam infrastructure that must function on immense scales and with extraordinary precision. The sail must remain aligned. The beam must remain coherent. The target craft must survive acceleration that may be extreme in both magnitude and sensitivity. These are not small demands. They merely differ from the burdens of carrying fuel. In this way, laser sails show that interstellar travel may involve trade rather than triumph. Mass can be reduced, but fragility increases. Travel time can shrink, but deceleration vanishes. The spacecraft can become faster, but also more limited in what it can do once it arrives. A probe may cross 1 light year, in a time that at last feels compatible with scientific ambition, yet the mission it performs will be narrower and more difficult than romantic imagination first suggests. That does not make the concept lesser, it makes it honest. Laser sails may become the first true interstellar tools precisely because they accept constraint, rather than trying to overcome every difficulty at once. They give up size comfort and return in exchange for speed. In doing so, they may become the earliest machines to cross distances that larger craft still cannot manage. 1 light year under this logic does not become easy. It becomes briefly passable for the smallest and most disciplined of travelers, driven not by onboard fire, but by light cast from home across the dark. By the time serious discussion reaches advanced engines, a hidden pattern begins to emerge beneath every proposal. The engines differ in fuel design and ambition, but they all struggle with the same underlying burden. Speed in space is never free. It must be purchased with energy mass and structure, and the price rises far more quickly than ordinary intuition expects. This is the point where the dream of 1 light year turns from a contest between engine types into a confrontation with the deeper accounting of motion itself. In everyday life, an increase in speed often feels simple. A stronger motor or a more efficient machine produces a faster result, and the improvement appears smooth, almost linear. Space does not behave that way for rockets. A rocket is not merely a vehicle pushed by an external surface. It must carry and throw away reaction mass in order to move. That requirement leads to one of the hardest principles in astronautics, often called the rocket equation. In plain terms, the faster a rocket wishes to go, the more propellant it must carry. But carrying more propellant makes the rocket heavier, which means even more propellant is required to move the added propellant. The demand compounds. Each gain in speed can require a disproportionate increase in fuel mass until the design begins to swell into absurdity. This is why rocket design feels so constrained even before interstellar travel is considered. The problem is not simply a lack of courage or imagination. It is that motion purchased by expelling mass becomes increasingly expensive as the desired velocity grows. For journeys within the solar system, engineers can still work within this logic by using staging gravity assists, efficient trajectories, and careful optimization. For 1 light year, the old arithmetic becomes brutal. A spacecraft intended to reach a meaningful fraction of the speed of light must either carry extraordinary energy or find some clever way to avoid carrying all the propellant itself. That is why so many proposals become strange as soon as they are taken seriously. The scale of the energy demand bends engineering toward extremes. Even before relativity enters the conversation, the numbers are severe. To accelerate a vehicle of significant mass to very high speed requires an amount of energy that dwarfs ordinary transportation by a staggering margin. This energy must be generated, stored, directed, and survived. It must not merely exist in abstract. It must become a physical system that operates without destroying itself. At modest spaceflight speeds, this challenge is already difficult. At interstellar ambitions, it becomes dominant. Engines are no longer judged only by whether they function. They are judged by whether the civilization building them can afford the energy economy required to use them. A starship is therefore not just a machine. It is a statement about the industrial depth of its makers, about the fraction of their resources they are willing to devote to motion across the dark. This is one reason why interstellar travel may depend not only on invention, but on scale of civilization. A society that can command vast energy flows across its home system might consider projects that a planet-bound civilization cannot. Yet even for such a society, higher speed remains punishing. Then, relativity begins to tighten the screws further. At speeds much lower than light, classical reasoning works well enough for most purposes. But as a spacecraft approaches a substantial fraction of light speed, the structure of the problem changes. The energy required to continue accelerating rises in a way that becomes increasingly harsh. Light speed is not just very fast. It is a fundamental limit built into the geometry of spacetime. Objects with mass cannot simply be pushed across it by adding enough fuel. The closer a spacecraft moves toward that boundary, the more stubborn the boundary becomes. The energy cost grows dramatically, and the dream of reaching or exceeding light speed retreats into impossibility under known physics. This is a crucial moment in the argument, because it reveals that interstellar difficulty is not only technological. It is woven into the architecture of reality itself. The stars are not separated merely by practical inconvenience. They are separated by a universe that allows fast motion only at extraordinary cost, and forbids the simplest fantasy of all the idea that one can keep accelerating in the ordinary way until the speed of light is passed. This realization gives sharper meaning to every earlier propulsion concept. Fusion seems hopeful because it may reach meaningful fractions of light speed, not because it can bypass the light barrier. Antimatter seems seductive because it offers enormous energy, not because it cancels relativistic cost. Laser sails seem clever because they shift where the energy is stored, not because they make energy unnecessary. Every serious concept remains inside the same universal bookkeeping. One can negotiate with the bill. One cannot abolish it. There is also a subtler cost hidden inside high speed. A spacecraft moving rapidly through interstellar space does not only require immense energy to accelerate, it also becomes a more dangerous object. Collisions with dust grains, exposure to radiation, and the management of waste heat all become more severe as velocity rises. Faster travel shortens time, but it also intensifies hazard. The machine must survive the very speed it seeks. Thus, the price of speed is paid twice, once in energy and once in protection. This dual cost helps explain why the road to 1 light year is so unforgiving. Every attempt to shorten the journey enlarges another burden elsewhere in the design. This does not mean the problem is hopeless. It means the problem is honest. The universe does not hand out distance cheaply. To move quickly between stars, a civilization must solve propulsion power, shielding materials, control, and long-term reliability together, because none can be separated from the others at high velocity. The stars therefore remain reachable only in a qualified sense. They may be reachable in principle, but only through systems so demanding that speed itself becomes a measure of civilizational depth. 1 light year is not merely a destination waiting for the right engine. It is a test of whether intelligence can accumulate enough disciplined power to buy time back from distance without being ruined by the cost of the purchase. That is the hidden meaning of propulsion at this level. The journey is never only about moving forward. It is about what must be spent, built, and endured to make forward motion possible at all. As propulsion concepts push closer to meaningful fractions of the speed of light, another transformation begins, one that feels at first almost gentle and then steadily more unsettling. Time itself no longer behaves in the simple, shared way familiar from ordinary life. In daily human experience, time appears to pass equally for everyone, except for the minor practical differences of clock schedules and location. A year feels like a year. Distance may separate people, but duration remains something assumed to be common. Relativity changes that assumption. When a spacecraft moves at high speed relative to Earth, the passage of time on board and the passage of time for those left behind are no longer identical. This is not illusion, and it is not merely a trick of measurement. It is a real feature of space-time confirmed by experiment many times over. Clocks in different conditions do not always accumulate time at the same rate. At everyday speeds, the difference is too small to notice. At interstellar speeds, the difference grows into one of the strangest consequences of all serious star travel. A journey may remain long in one frame of reference and become shorter in another. This is where the phrase time dilation enters the discussion. In simple terms, a traveler moving at very high velocity experiences less elapsed time than observers who remain behind. The closer the traveler's speed comes to that of light, the stronger this effect becomes. From the perspective of Earth, a spacecraft may require many years to cross 1 light year. From the perspective of those aboard, the subjective duration may be less. The distance itself also changes in the traveler's frame through a related effect often called length contraction, where the separation in the direction of motion appears reduced. Together, these effects create one of the rare places in physics where the stars seem to soften slightly. The universe still forbids travel faster than light, but it does allow the internal experience of a long journey to become shorter if enough speed is achieved. This is why relativity can sound almost merciful after the brutal accounting of propulsion. It appears to offer a hidden gift. 1 light year may remain, 1 light year for Earth, but for those moving fast enough, the journey can feel less severe. Yet the comfort is incomplete and carries a profound emotional cost. The spacecraft may arrive with its crew having aged only a limited number of years, but far more time may have passed at home. Families, cultures, political systems, languages, and perhaps entire civilizations can shift during the interval. The travelers preserve their personal duration at the price of separation from the world that launched them. This makes relativistic travel unlike any voyage in ordinary history. A sailor crossing an ocean may return older and changed, but still to a recognizable homeland. A traveler moving near light speed may return to a future in which the original society exists only as memory archive or distant ancestor. Time dilation, therefore, does not erase the difficulty of 1 light year. It redistributes it. It gives some time back to the travelers while taking shared time away from human continuity. This has deep implications for how interstellar missions are imagined. A fast voyage is not simply a matter of better convenience. It alters the relationship between mission and civilization. If a crew departs for another star system at relativistic speed, the mission may remain coherent to them, but the homeworld may move on through decades or centuries that they do not fully share. Communication also becomes complicated by distance and delay. Even messages sent at light speed still require years to cross interstellar space. There is no conversation in the ordinary sense, only correspondence stretched across silence. For a traveler moving fast and a civilization remaining behind, there can emerge a widening gap, not only of place, but of history. The journey becomes a one-way thinning of common time. This helps explain why relativistic travel is both scientifically fascinating and culturally difficult. It offers a path toward humanly survivable durations on board, while simultaneously undermining the familiar meaning of departure and return. A mission may succeed in engineering terms and still dissolve the old social idea of homecoming. There is also an important restraint within all this. Time dilation does not help much at modest speeds. It becomes significant only when velocity approaches a substantial fraction of light speed, which means the energy burden described earlier remains fully in force. Relativity offers no free shortcut. It becomes relevant only when a civilization has already paid dearly to move fast. In that sense, the effect is not an escape from the problem of propulsion, but a companion to it. One earns the strange bending of time only by entering a regime where energy shielding and engineering requirements grow severe. This is why discussions of time dilation can sometimes mislead when separated from the larger context. It is true that a traveler might cross great distances within a shortened personal timespan. It is equally true that reaching the speed required for such a benefit may itself be among the hardest technological achievements a civilization can pursue. The physics is generous in one domain and harsh in another. Even so, relativity changes the emotional architecture of interstellar thought. Before it enters one light year appears as a fixed prison of duration, a distance to be endured in the same temporal currency by all involved. After it enters, the prison becomes asymmetrical. Time can be experienced differently depending on motion. This does not reduce the universe to kindness, but it does reveal a more subtle structure than intuition first suggests. A star may remain unreachable in the old communal sense, and yet reachable in a deeply altered personal one. That duality matters. It means that interstellar travel, if it ever becomes possible, may not simply be transportation on a larger map. It may become a form of migration across different rates of lived time, where the travelers and the civilization that sends them begin together and then steadily fall out of temporal alignment. In that possibility lies one of the most haunting truths of all. The road to the stars may not only separate people from places, it may separate them from the shared flow of history itself. Interstellar space is often described as empty and compared with planets' atmospheres or even the denser regions of a solar system. That description is broadly fair. The space between stars contains very little matter. There is no air, no weather, no familiar terrain, no sheltering magnetic field extending from a nearby world. At first glance, this emptiness seems almost helpful. If there is so little there, then perhaps a spacecraft crossing one light year would move through a kind of perfect silence, troubled mainly by its own machinery and the length of the route. But this impression does not survive careful thought. In the environment of interstellar travel, emptiness is not safety. It is exposure. A place can be nearly empty and still deeply hostile, especially when a vehicle moves through it at very high speed for years or decades. The hazards are subtle, distributed, and relentless. They do not always come in dramatic impacts or visible storms. Often they appear as the slow wearing effect of radiation, the hidden risk of dust, the cumulative burden of heat management, and the difficulty of shielding life or equipment in a region where there is nothing nearby to hide behind. This is one of the important reversals in serious starflight thinking. The phrase empty space sounds peaceful, but the longer one considers it, the more it resembles a field of continuous vulnerability. One of the first dangers is radiation. Space within the solar system already exposes spacecraft and astronauts to energetic particles from the sun and from distant cosmic sources. Beyond the protective effects of Earth's atmosphere and magnetic field, that exposure becomes a major operational concern. In interstellar space, far from planetary shelter and often far from any strong local magnetic environment, a spacecraft must endure radiation over long durations with no natural refuge. Galactic cosmic rays, which are high-energy particles arriving from violent astrophysical processes across the galaxy, can penetrate materials and damage electronics, degrade sensors, and pose serious biological risks to living tissue. A single event may not destroy a mission, but the accumulated exposure over time can alter materials, increase failure rates, and raise the risk of long-term harm to any crew. Shielding helps, but shielding adds mass and mass returns immediately to the propulsion problem. Thick protective layers may be possible for some robotic missions or for carefully designed habitats, yet every kilogram included for safety must also be accelerated across the dark. The environment therefore forces a difficult balance between protection and practicality. Then there is dust, a danger that sounds minor until velocity is considered. The interstellar medium is thin, but it is not a perfect vacuum. There are atoms, ions, and tiny grains of matter scattered through it. At ordinary speeds, such sparse material may pose little threat. At relativistic or near-relativistic speeds, even a minute particle can strike with extraordinary energy. A grain of dust encountered by a fast-moving spacecraft does not behave like ordinary dust. It becomes, in effect, a microscopic projectile. Repeated over a long journey, these impacts can erode surfaces, damage sensors, threaten sails, and force engineers to think carefully about the geometry of the craft. Front-facing surfaces may require sacrificial shielding. Sensitive systems may need to be buried deeper behind protective mass. Some mission designs may even rely on forward dust clouds or magnetic fields to reduce the impact risk, though such methods introduce further complexity. The essential point remains the same. Empty space is not empty enough to ignore when speed rises. A vehicle capable of crossing 1 light-year quickly must survive not only distance, but collision with the faint material hidden inside that distance. Heat presents another challenge, although in a counterintuitive way. Space is cold in the sense that it lacks warm surrounding matter, yet a spacecraft cannot simply release heat whenever it wishes. In an atmosphere, heat can be carried away by moving air. In vacuum, the main path outward is radiation. High-power engines, onboard reactors, electronics, life support systems, and shielding interactions all generate heat that must be rejected to avoid damaging the vehicle. Radiators take space en masse and may be vulnerable. A machine built for interstellar travel therefore faces a strange thermal condition. It moves through the cold while struggling not to overheat itself. This is especially true for advanced propulsion systems, where enormous energy use tends to create enormous thermal management demands. The farther a mission reaches into serious starflight, the less the spacecraft resembles a simple vessel, and the more it resembles a careful negotiation among propulsion, shielding, cooling, and structure. Communication also becomes part of the hazard, though less physical than the others. As a craft moves deeper into interstellar space, delays grow from minutes to hours, then to days, then to years. Signals weaken with distance. Antennas must remain precise. Power must remain available. Faults cannot be corrected in real time. The spacecraft must increasingly become autonomous, capable of managing anomalies without immediate human guidance. In that sense, interstellar space tests not only the durability of materials, but the independence of systems. A machine crossing 1 light-year cannot depend on constant supervision from home. It must survive long silence while continuing to operate coherently in a hostile environment. For human travelers, the environment grows even more demanding. Radiation threatens biology as well as hardware. Psychological isolation joins physical danger. Closed habitats must remain stable. Medical problems cannot rely on quick return or rescue. The outside emptiness presses inward, not only as a physical condition, but as a total context of exposure with no nearby world to offer repair, resupply, or refuge. All of this alters the emotional meaning of the journey. 1 light year is not merely a line to be crossed by a sufficiently fast engine. It is a volume of hazard that must be inhabited, endured, or survived for the entire passage. The interstellar medium may be tenuous, but over enough distance and enough speed, tenuous becomes consequential. The darkness between stars is not a blank page. It is a harsh environment, written in sparse matter, penetrating radiation, thermal difficulty, and silence. A successful starship must therefore do more than move quickly. It must remain intact while crossing a region that offers almost nothing in the way of forgiveness. The emptiness itself becomes part of the obstacle, and the deeper the journey goes, the clearer it becomes that between the stars there is not peace, but a long and exposed test of everything a spacecraft is built to withstand. When the known burdens of propulsion, energy, radiation, and time have been faced directly, the imagination often turns toward ideas that seem to offer escape not by endurance, but by cleverness, as though the universe might contain a hidden door after all. These concepts stand at the edge of serious physics and speculative hope. They are not always foolish, and some arise from genuine equations within relativity or plasma theory, yet they occupy a precarious region where mathematical possibility does not easily become physical reality. Among them are concepts such as the Bussard-Ramjet warp drives and wormholes. Each attracts attention because it appears to answer one of the central agonies of interstellar travel. The Bussard-Ramjet tries to solve the fuel problem by gathering hydrogen from interstellar space as the spacecraft moves, using that material as fusion fuel rather than carrying all propellant from the start. Warp drive ideas try to solve the speed limit problem by altering space-time itself, allowing a craft to ride within a region of contracted space ahead and expanded space behind. Wormholes, at least in theory, try to solve distance more radically still by connecting remote regions of space-time through a shortcut, turning the long road between stars into a much shorter passage. These ideas have extraordinary narrative appeal because they seem not merely to improve current travel, but to remove the most painful constraints altogether. Yet this is precisely why they demand careful scrutiny. When a concept appears to sweep away the hardest parts of the problem, it often does so by introducing difficulties of another and more fundamental kind. The Bussard-Ramjet is a useful example because it begins from a physically grounded intuition. Interstellar space, though thin, does contain hydrogen. A spacecraft moving through that medium might in principle use a vast magnetic scoop or related mechanism to collect charged particles, compress them, and feed them into a fusion engine. In the ideal form of the concept, the vehicle would draw fuel from the path ahead, reducing the impossible burden of carrying everything from launch. This is elegant in theory. It turns the interstellar medium from hazard into resource. But the difficulty emerges quickly. The density of hydrogen between stars is extremely low. Gathering enough material to matter would require an enormous collection field, and even then the drag associated with sweeping particles from the medium may offset much of the gained benefit. Compression ignition and sustained fusion of the collected material create additional challenges. Some analyses suggest that the concept struggles to provide net advantage under realistic conditions. In other words, the universe may offer fuel in the road, but in such thin supply and under such difficult circumstances that the road still cannot easily be traveled. The idea remains instructive because it shows how a beautifully self-sustaining concept can falter when real densities, reaction thresholds, and drag are included. Warp drives push farther outward into speculation. Certain solutions to the equations of general relativity have suggested that space-time geometry might permit regions moving effectively faster than light, relative to distant observers, without violating the local rule that nothing with mass outruns light in its own immediate frame. This is the source of the famous notion that a craft could remain locally at rest inside a bubble while space itself carries it. As an image, it is almost irresistible. It preserves relativity while seeming to bypass its harshest practical implication. Yet the gap between mathematical allowance and physical realization is severe. Proposed warp metrics often require exotic energy conditions, including forms of negative energy density not known to exist in the needed quantities. They may also involve stability problems, horizon problems, or energy demands, so enormous that the concept loses practical meaning. Some later work has explored whether the requirements might be reduced, but reduction is not removal. A concept can move from absurdly impossible to less absurdly impossible and still remain far beyond credible engineering. The same caution applies to wormholes. General relativity allows the language in which such structures can be described, but keeping a traversable wormhole open appears to require matter or energy with properties not available in any ordinary sense. Even if such exotic support existed, there would remain profound questions about formation stability, causality, and interaction with real physical systems. One does not build a shortcut through space-time in the same way one builds a bridge. The entire framework of the problem lives at a scale where known engineering becomes almost irrelevant before deeper physical uncertainties. This is why exotic escape concepts are so revealing. They do not merely test the imagination, they test the boundary between equations and existence. A metric can be written and still describe something no civilization will ever construct. A loophole can appear in theory while remaining closed in nature. That distinction matters deeply when asking how long it would take to travel 1 light year. If the answer depends on warp drives or wormholes, then under present knowledge, the practical answer remains that 1 light year is not traversed that way at all. It remains subject to engines' energy shielding and time. This does not mean exotic ideas are worthless. On the contrary, they can sharpen understanding by showing exactly where known physics becomes restrictive and where the desire for shortcuts grows strongest. They remind the mind that the stars provoke not only engineering, but the longing to discover that the universe is kinder than it first appears. But serious thought must permit the opposite possibility, as well that the universe is elegant without being accommodating. The laws of nature may allow extraordinary structures in equations while denying them to practical civilizations. The gap between could be described and could be built, may be the final and sobering truth behind many interstellar fantasies. Even the most imaginative species must live not in its preferences, but in the actual generosity or severity of the cosmos it inhabits. Exotic concepts, therefore, occupy an important but limited place. They are useful as probes of theoretical space, as ways of asking how rigid the light barrier truly is, and whether the geometry of space-time hides any deep permissiveness. yet they do not currently provide a dependable path. They are reminders that some ideas remain beautiful precisely because they have not yet been forced to survive materials, science, thermodynamics, field stability, or industrial reality. 1 light year seen through them briefly appears negotiable. Then the mathematics recedes, and the old barriers return. The stars remain where they are separated by distances that still demand actual motion through actual space, unless nature proves stranger and more generous than evidence now suggests. If the problem of interstellar travel cannot be solved by ever smaller probes or by hypothetical shortcuts through space-time, then one of the oldest and most stubborn answers returns with greater force. Instead of asking how to make the journey short enough for a human life, the question becomes how to make human life durable enough for the journey. This is the logic behind the generation ship, a concept both practical in its refusal to depend on miracles and unsettling in the scale of transformation it demands. A generation ship is not simply a spacecraft with passengers. It is a moving world, an enclosed society intended to remain alive and coherent across spans so long that those who arrive may be the distant descendants of those who departed. At once, the center of the problem shifts. Engines remain important, but the dominant challenge becomes not propulsion alone. It becomes continuity. A ship that must travel for centuries through the dark must carry more than fuel structure and instruments. It must carry an ecology, a culture, a memory system, a political order, a method of education, and some durable answer to the question of why the mission continues. This is where interstellar travel becomes fully civilizational. The spacecraft ceases to be a machine, transporting a community, and becomes the community itself. Everything that would normally be external on a planet must now be reproduced inside a bounded artificial environment. Air must be renewed. Water must be purified and recirculated. Nutrients must return through closed loops. Waste cannot simply be discarded and forgotten. It remains inside the same limited world and must become part of a larger cycle. Agriculture, or some equally reliable food production system, must persist under stable conditions for generation after generation. Lighting temperature, microbial balance, pollination, disease control, and material maintenance all become matters not of convenience, but of survival. A generation ship therefore resembles a spacecraft and an ecosystem at the same time, and both dimensions must remain functional without the forgiving backdrop that planets provide for free. On Earth, failures in one region can be offset by abundance elsewhere. On a generation ship, there is no elsewhere. Every imbalance is local and persistent. This makes ecological design one of the deepest requirements of the mission. The ship must be closed enough to survive and flexible enough to absorb error. It must withstand both technical breakdown and biological drift, the slow ways in which living systems change under prolonged confinement. Then there is the problem of maintenance. Machines built for decades already face fatigue, corrosion, wear, software decay, and the loss of manufacturing support. A vessel intended to persist for centuries must do more than resist breakdown. It must contain the means of diagnosing, repairing, and perhaps rebuilding itself. Spare parts alone are not enough. Raw materials, fabrication systems, technical knowledge, and a culture of upkeep all become essential. The ship must, in effect, become an industrial habitat capable of reproducing not only life, but competence. Skills cannot be left in manuals alone. They must be transmitted through education and practice. Future generations must understand systems they did not design and preserve a mission they did not choose. This introduces a social complexity at least as serious as the engineering one. A generation ship cannot depend on short-term motivation. It must transform purpose into tradition. Children born aboard would not experience the voyage as an expedition. They would experience it as normal life. The destination might appear to them as a historical obligation, a sacred idea, a civic project, or perhaps a distant abstraction. The departure world might feel equally abstract, a place from ancestral memory rather than personal reality. This means the mission must be legible across changing identities. It must survive reinterpretation without losing coherence altogether. Governance, therefore, becomes crucial. A society in transit for centuries must manage disagreement, scarcity, leadership succession, and collective discipline without fragmenting. Too much rigidity could turn the ship into a brittle hierarchy unable to adapt. Too much freedom could dissolve common purpose and threaten systems that require careful coordination. The political structure must therefore achieve something rare, long-term stability without suffocating renewal. That difficulty may prove one of the greatest of all. Human societies on planets have often struggled to remain peaceful and coherent over far shorter spans and under far less confined conditions. A generation ship would compress these tensions inside a sealed environment where failure has no outside escape. Questions of justice would become practical questions of survival. The same is true of genetics and population health. A multi-generational mission must preserve enough biological diversity to avoid severe inbreeding and must maintain medical capacity across long durations. Reproduction cannot be treated as merely personal. It becomes part of mission design. This raises moral challenges immediately. How much freedom can individuals retain when population size must remain within ecological limits and genetic health must be protected? A generation ship cannot simply copy the social assumptions of planetary life. It would require forms of planning consent and cultural adaptation that many existing societies might find uncomfortable. Yet ignoring those issues would not make them disappear. The closed nature of the voyage forces every latent dependency into view. Education also changes character aboard such a vessel. It is no longer preparation for participation in a broader world. It is preparation for stewardship of a single fragile world in motion. Children would need to learn engineering, ecology, history, medicine, and governance, not as specialized disciplines removed from daily life, but as the practical grammar of survival. The ship's archives would matter not only as records, but as anchors of continuity, preserving why the journey began and how earlier generations understood their condition. Without such memory, systems drift could become forgetfulness, and forgetfulness could become danger. A generation ship therefore teaches one of the deepest lessons of interstellar thought. If the stars are too far for individuals, then the unit of travel may cease to be the person and become the society. 1 light year under this logic is no longer a route crossed by explorers. It is an interval inhabited by a civilization in miniature. The journey becomes a test, not only of technology, but of whether a human community can remain alive, competent, ethical, and meaningful, while cut off from every planetary foundation that shaped the species in the first place. In this form, interstellar travel does not look like escape. It looks like the hardest experiment in civilization ever imagined. Once a generation ship is imagined in enough detail to feel structurally possible, another difficulty rises from within it, quieter than propulsion, and less visible than shielding, yet equally capable of deciding whether the mission endures. This is the problem of meaning across time. A spacecraft can preserve air, water, and machinery with sufficient discipline. It can even preserve a population if its ecology and governance remain stable. But whether it can preserve purpose is a deeper and less mechanical question. The people who begin the voyage and the people who continue it are not the same. They do not share the same horizon of memory, sacrifice, or desire. For the founders, the mission may be urgent, chosen, and historically legible. They know the departure world directly. They understand the dangers that made departure necessary, or the ambitions that made it worthwhile. They may accept confinement because it serves a goal they consciously endorse. For their descendants, the conditions are entirely different. Life aboard the ship is not a chosen expedition, but the inherited structure of reality. The mission is no longer an act. It is an environment. The destination is no longer a target glimpsed by those who once looked up from Earth. It is a concept received through education, ritual, law, and narrative. This difference matters because continuity of function is not the same as continuity of belief. A society can remain alive while slowly forgetting why it is moving. At that point, the most advanced starship ever built begins to face an ancient human problem, the problem of transmitting commitment across generations that did not consent to the original bargain. Every civilization on Earth already struggles with this in smaller forms. Institutions inherit goals established by the dead. Nations preserve founding stories that later citizens did not witness. Religions, constitutions, and long infrastructure projects all depend on memory extended beyond individual lives. Yet on a planet, such continuity exists within a wide environment where alternatives remain available. People can emigrate, dissent, detach, or reinvent. On a generation ship, the environment is sealed. There is no broader world to absorb drift. If purpose erodes, there is no external structure to carry the mission forward automatically. The ship must therefore cultivate not only knowledge, but legitimacy. Future generations must feel that the voyage still belongs to them in some meaningful sense. This requirement creates a delicate tension. A mission that relies entirely on rigid indoctrination may preserve obedience while hollowing out authenticity. A mission that allows unrestricted reinterpretation may gradually lose coherence and divide into incompatible ways of understanding the journey. Somewhere between these extremes lies the social art the ship must master. It must keep the destination real enough to guide action while allowing the living culture aboard to remain genuinely alive rather than frozen in ancestral command. This is why narrative becomes operational. Stories, commemorations, archives, and civic rituals are not decorative additions to the voyage. They may be among the systems that keep it intact. A child born aboard such a vessel would need to inherit not merely technical information, but a map of belonging, an answer to where the community is in history and why its current sacrifices matter. Without that, maintenance becomes drudgery. Without context, discipline becomes arbitrary, and the future becomes too abstract to govern the present. Yet the problem cuts deeper still. Over centuries, the community may change so thoroughly that the destination itself loses some of its original meaning. The conditions that justified departure may no longer apply. The values of the descendants may differ from those of the founders. Scientific knowledge may evolve. The mission's central purpose may be reinterpreted from survival to duty, from duty to curiosity, from curiosity to identity. At some point, the ship may cease to think of itself as traveling from one world to another, and instead think of itself as a world whose motion is simply part of its nature. This is not necessarily failure. It may even be a sign of healthy adaptation. But it raises a profound question. If a generation ship eventually becomes a self-contained civilization, with its own culture priorities and definition of home, is arrival still the same mission that departure began? The names may remain, the trajectory may remain, the meaning may not. In that sense, one light year traveled over generations is not just a spatial crossing. It is a transformation of collective identity. The ship moves through the dark while history happens inside it. There may be reform movements, periods of unrest, religious awakenings, philosophical schools, artistic traditions, and changes in law, all unfolding within the same vessel that engineers once described, mainly in terms of thrust mass and shielding. A true interstellar voyage therefore becomes inseparable from social evolution. This creates another layer of uncertainty. The success of the mission may depend less on whether the original plan was perfect, and more on whether the society aboard remains capable of revising itself without collapsing. Resilience may matter more than purity of design. A culture able to repair not only machines, but meanings may endure better than one that treats the founding blueprint as untouchable. There is also the question of whether the destination should remain compulsory. If generations pass and the society aboard becomes stable, flourishing and internally complete, would its members be morally obliged to continue toward a world chosen by distant ancestors? Or would they have the right to redefine their future, perhaps slowing, redirecting, or even abandoning arrival if the costs no longer make sense? This question reveals how interstellar travel can shift from an engineering ambition into a problem of political philosophy. A ship designed to preserve life may eventually have to decide whose authority governs life's direction when the original authors are long gone. The farther one follows this line of thought, the clearer it becomes that star travel across centuries is not a single mission extended in time. It is many missions layered atop one another, each generation inheriting a trajectory and deciding again explicitly or silently whether to renew it. One light year then becomes not just a distance between stars, but a duration during which a civilization repeatedly negotiates with itself. The ship survives not merely by holding together structurally, but by continually answering the question of whether movement still has meaning. In that answer lies one of the most fragile systems aboard, more difficult to engineer than engines, and more decisive than almost any component made of metal. A society can endure confinement, scarcity, and labor if it believes the future remains coherent. If that coherence breaks, the dark outside may not be what ends the mission. The unraveling may come from within through the slow loss of a shared reason to keep going. After engines, radiation time, dilation, closed ecologies, and the continuity of meaning have all been considered, the argument begins to turn back toward the place where the journey starts. This return is important because interstellar travel is often imagined as though the central question is simply whether a species can reach another star. In practice, another question may come first. Why would it try, and at what stage of development would such an attempt be wiser than building more completely within its own system? One light year looks different when viewed not from the deck of a hypothetical ship, but from the perspective of economics, infrastructure, and long-term strategy. A civilization does not move outward into the stars as a single heroic act. It expands through capacities. It learns to use energy on larger scales, to build reliable systems away from its birth world, to coordinate resources across distance, and to preserve knowledge and production through time. By that measure, humanity remains at a very early stage. It has reached orbit, walked briefly on the Moon, placed machines across parts of the solar system, and begun to imagine permanent activity beyond Earth. These are remarkable beginnings, but they are still beginnings. The solar system itself remains largely untouched, a vast region rich in sunlight materials, orbital space, and scientific opportunity. Before speaking confidently of another star, a sober analysis must notice how much remains unfinished at home. This is not an argument against ambition, it is an argument about sequence. The inner and outer regions of the solar system contain worlds, moons, asteroids, and energy resources that could occupy centuries of development. Habitats might be built in orbit. Industry might move partly off Earth. Mining, manufacturing, and power generation could spread across multiple environments. Scientific settlements might appear on the Moon Mars, or within free-floating structures designed specifically for human life, rather than adapted to planetary surfaces. None of this is easy, but compared with interstellar travel, it lies within a far more forgiving envelope. Communication delays remain manageable within most of the solar system. Rescue, resupply, and redesign remain conceptually possible. Energetic demands, though still substantial, are vastly lower than those required to push ships toward significant fractions of light speed. This difference matters because civilizations often advance not by skipping difficulty, but by mastering adjacent layers of difficulty in sequence. In that sense, the solar system may not be a waiting room for the stars. It may be the main arena of human expansion for a very long time. If so, then the most realistic future may not be one in which humanity quickly escapes the solar system, but one in which it becomes deeply distributed within it. Such a civilization could still achieve enormous range compared with present life. It could spread across millions or even billions of kilometers while remaining under the influence of one star. To a planet-bound species, that would already feel vast. Entire cultures might grow in different gravitational settings and around different worlds. Economic networks might span planetary orbits. Scientific attention could reach to icy moons, dwarf planets, and the fringes where interstellar space begins. The local neighborhood of the Sun is so large that fully inhabiting it may itself represent a multi-era project. This is where the practical case against rapid interstellar migration becomes strongest. The nearest stars are not merely far. They are far in a way that multiplies cost without necessarily multiplying usefulness on early timescales. A civilization able to build a durable solar system economy may gain more benefit from extending that economy outward within its own system than from sending extraordinarily costly missions to another star that may offer no immediate support, no guaranteed habitable world, and no possibility of timely exchange. The delay of communication alone changes the logic of coordination. Even at light speed, messages to a nearby star require years. Trade in any ordinary sense collapses under such delay. Governance becomes radically decentralized or meaningless across that gap. Cultural continuity weakens. An interstellar colony, if established, would not feel like an extension of the home system for long. It would become its own isolated branch of civilization. This may happen eventually, but it is not the same as expanding a coherent network. The solar system, by contrast, still allows delayed but recognizable connectedness. There is also the issue of risk. A civilization that has not yet learned to sustain complex, long-duration life support and industry across its own system may be poorly prepared to attempt star travel responsibly. Interstellar missions magnify every failure mode. Ecological instability, governance, breakdown material, fatigue, radiation exposure, and mission drift all become harder when no nearby world can assist. From this perspective, Remaining solar for a long time is not evidence of weakness. It may be evidence of prudence. The path to the stars, if it exists at all, likely runs through a mature phase of solar system civilization, where the tools, surplus energy, industrial capacity, and cultural depth required for starflight are built gradually from smaller successes. This suggests a more modest but more plausible picture of humanity's future. Rather than seeing the solar system as a cage to be escaped quickly, one can see it as the first and possibly sufficient sphere of flourishing. A species may live richly within one stellar system for immense stretches of time, building habitats in places with no natural atmosphere, reshaping asteroids into settlements, harvesting sunlight on scales currently hard to imagine, and studying the galaxy from many vantage points without physically crossing to it. Under this view, the stars remain objects of science inspiration and perhaps eventual contact, but not necessarily destinations of immediate migration. 1 light year then becomes a boundary not only of distance but of strategic meaning. It marks the point where the logic of local expansion begins to give way to something harsher, slower, and more discontinuous. This does not prove that humanity will never leave the solar system. It suggests that if departure happens, it may come much later than popular imagination prefers, after the species has become not merely spacefaring, but system-building. Until then, the most realistic future may lie in going deeper into the sun's domain rather than beyond it. The irony is that such a future could still be immense. Humanity may remain solar and yet inhabit a realm so broad and varied that earlier ages would have called it cosmic. The cage, if it is one, is far larger than the word suggests. Yet, compared with the stars, it may still be a cage, and knowing that may shape the long mood of civilization even as it learns to live fully inside it. At the far end of all these calculations, beyond the engines and equations, beyond the reactors, sails, shields, and social designs, there remains a quieter question about what it means to confront a universe that may be knowable far beyond what it is physically traversable. 1 light year began as a distance, a simple unit defined by the path of light in a year. By the time the full weight of that measure has unfolded, it has become something larger. It has become a mirror held up to the condition of an intelligent species, born on a planet asking how far understanding can outrun embodiment. The answer, at least for now, is that thought travels farther than hardware. Observation reaches farther than bodies. Knowledge arrives where presence cannot. This may sound like a consolation prize, but it is not a small thing. In many ways, it is already the primary mode by which the universe becomes part of human life. Long before any spacecraft leaves the solar system, in a meaningful interstellar sense, telescopes gather light from distant stars, planets, nebulae, and galaxies. Spectra reveal composition. Motion reveals mass. Variations in brightness reveal orbiting worlds. Radio signals, infrared maps, and gravitational measurements expose structures no hand will ever touch. Through these methods, human beings have learned the temperatures of remote stars, the chemistry of far atmospheres, the existence of planets around suns that no ship has approached, and the large-scale history of a universe whose oldest light began traveling long before Earth formed. This is an astonishing situation. A species with feet adapted to soil and lungs adapted to air has discovered how to read realities spread across millions and billions of light years. In that sense, the limits of travel have never been the limits of contact. Light itself carries news. Physics provides the grammar. Instruments become the means by which the distant enters the local mind. Seen this way, 1 light year is not merely an obstacle. It is also a bridge because the same distance that prevents easy travel still allows information to cross. The stars may remain unreachable in the bodily sense, yet they are not sealed away from knowledge. This distinction matters because it reframes the emotional outcome of the whole inquiry. If the argument ended only with confinement, it would be too simple. It would describe the universe as a field of forbidden destinations and leave intelligence staring outward at an inaccessible beauty. But intelligence has already found another way to participate. It studies models, simulates, compares infos, and listens. It builds observatories on mountains, in deserts, in orbit, and at the quiet edges of radio noise. It sends robotic instruments where humans cannot yet go and receives from them measurements that change the shape of thought on Earth. In time, it may send tiny interstellar probes, not as settlers, but as messengers of curiosity. Even these partial acts matter. They show that the failure to inhabit a distant place is not the same as ignorance of it. The universe can be deeply known without being fully crossed. There is humility in this realization, but also a strange enlargement. A species need not conquer the stars to be transformed by them. It need only understand enough to place itself correctly among them. This may be one of the deepest gifts of astronomy and space science. They do not simply promise travel, they teach proportion. They reveal that the human story unfolds inside a structure at once indifferent and intelligible vast, beyond migration, perhaps yet transparent enough in parts to be studied. The inability to move freely across that structure does not cancel the grandeur of understanding it. In some respects, the grandeur becomes sharper because motion is difficult. Knowledge earned without possession often carries a cleaner kind of respect. There is also the possibility that limitation itself shapes civilization in fruitful ways. A species that cannot easily flee to another star may learn to care more carefully for its own worlds, to build more sustainably within its own system, and to value observation over conquest. This is not guaranteed, but the physical difficulty of escape may impose a moral seriousness that abundance would not. If the solar system is the primary sphere of life for a very long time, then learning to flourish within it becomes a mature project rather than a disappointing compromise. The stars remain guides, not because they await quick settlement, but because they continually enlarge the horizon of what can be asked and known. Even the search for alien life belongs here. It matters not only because contact or travel might someday occur, but because evidence of life elsewhere would alter the meaning of human existence, regardless of whether the gulf can be crossed. To know that life arose around another star would be an intellectual event of enormous consequence, even if no person ever stands there. This is the final inversion hidden inside one light year. What seems at first like a story about motion ends as a story about relation. The universe may deny easy passage while still allowing deep connection through evidence, law, and light. It may keep the stars physically remote while making them mentally intimate. That intimacy is real. It shapes philosophy, science, art, and the long self-understanding of civilization. The night sky is not merely decoration above a trapped species. It is an active source of orientation, telling Earth-born minds where they are, how large the surrounding structure is, how old the cosmos has become, and how delicate the conditions of life may be. If interstellar travel remains rare, partial, or forever out of reach for large human communities, the stars will still matter with undiminished force. They will matter because they continue to instruct. 1 light year in the end is both a wall and a teacher. It says that the universe is not arranged for convenience. It says that intelligence must negotiate honestly with scale. But it also says that understanding can cross places where bodies cannot, and that a civilization may remain physically local while becoming intellectually cosmic. In that possibility, there is no defeat, only a different kind of reach, quieter than starships, slower than fiction, and perhaps more enduring than either. The stars remain in their places above the long turning of Earth, and the distance to them remains unchanged by desire. 1 light year is still what it is, a span so large that even the boldest engines of the present age barely begin to answer it. Chemical fire fades too quickly. Nuclear power offers force, but carries heavy burdens. Fusion suggests a future that may one day compress the dark into something survivable. Antimatter glows at the edge of feasibility. Laser sails may send tiny messengers ahead of any human body. Relativity reshapes time without removing the cost of speed. Generation ships transform travel into civilization. The solar system itself appears less like a threshold and more like a vast first home, perhaps large enough to occupy the species for ages before any true departure becomes possible. Yet none of this leaves the journey empty of meaning. Light continues to cross the gulf even when ships do not. Telescopes gather distant worlds into knowledge. Instruments and thought move outward by other means, turning remoteness into understanding. The universe may not permit easy passage between stars, but it still allows contact through evidence law and patient observation. In that quieter relationship, there is still wonder. A species may remain close to its sun and still learn the shape of the wider dark. It may never move freely among the stars, and yet still become changed by them, guided by them, and measured against their scale. The night sky does not become smaller because it is hard to reach. It becomes more honest. It reveals both the limits of motion and the reach of the mind, and in that tension, the human story continues local in body, perhaps, but never fully confined in thought.